Now we're looking at a teaching video, and the topic is applications of differentiation, in particular formulation for maxima and minima. It is very important for this particular topic, maxima and minima, for students to be able to formulate any rules. But in order to formulate the rules, the students must know the mensuration formulae for most of the objects and figures. So here I will just be focusing on objects. The first one I'm looking at is sphere, basically a ball shape. Well, the formula for the volume of a sphere would be 4/3 pi r cubed. Of course, if I'm looking at half of the sphere, then I'll just divide this expression by 2. So I'll get 2/3 pi r cubed. For surface area, let me just use A to denote surface area. Then it will be 4 pi r squared. Now, in a later time, I'll be looking at the surface area formula for hemisphere, half of a sphere. So it's not so straightforward as to think that this expression be divided by 2. Now next, I'm looking at cylinder. So many objects come in the form of cylinder, like rod, like the top part of the test tube. So we have to recognize the composite solid that we're given. So it could be a combination of a few of these solids. But for cylinder, the volume formula would be that of a prism, because a cylinder is a prism. If you just slice this body across this way, you find that each cross section will have the same area. Therefore, that is a prism. For a prism, the general formula would be base area times height. So in this case, the base area is a circular area, pi r squared, and the height is h. Next, when I look for the surface area of a cylinder, it is important to note which part of the formula refer to which particular surface area. For instance, if I'm talking about the top and bottom circular surface area, the top one is one of an area of a circle, which is pi r squared. So if I have two of those areas, then it will be 2 pi r squared plus, of course, the curved surface area, which is just the circumference of the base times the height. The circumference would be 2 pi r and the height is h. So bear in mind over here that this refers to the two circular faces. And here I have the curved surface. So the reason why it's important to take time to understand this is because sometimes you can have an open cylindrical container. So what it means is that we will only consider the bottom circular surface and not the top, because the top is removed. So when we read a question, open cylindrical cylinder, it means we will consider only pi r squared, not 2 pi r squared. Now we look at the third one, cone. You can see the two edges here will merge to a point, and that is called the vertex. So that is a vertex. So if you have this arrangement, just like in the case of pyramid, then the formula for the volume will be a third. So 1/3 the base area, which is a circular area, so I have pi r squared, then times the height. So 1/3 pi r squared h. And you notice that this particular part, pi r squared h, is actually the formula for the volume formula for a cylinder. So we would say that with the same radius and the same height compared to the cylindrical container, then the volume of the cone is always 1/3 the volume of the cylinder. So in this case, you can see this is the volume formula for a cylinder. Next, for the surface area, we will have the base area, which is pi r squared, then add on to the curved surface area, which is just pi rl. L here is referring to the slant height, and there is a relationship between R, H, and L. And if I just construct a right angle triangle, then you notice that the relationship will be L squared equals to R squared plus H squared. So some of this is important to take note of. So over here, that will be the curved surface area. And the top one, pi r squared, is the base area. Now we come to a hemisphere, which is half of a sphere. So the volume formula will be half of 4/3 pi r cubed. So I will have 2/3 pi r cubed. As for the surface area, now the surface area of a sphere is 4 pi r squared. Half of it will be 2 pi r squared. But there is the top surface as well, the circular surface, which is pi r squared. So they can be added together. So I have 3 pi r squared. So this is referring to the curved surface, just like that. And this is just the top surface area. Now we look at proof and formulation. So sometimes you're given an object like that, and I call it a composite object because it's basically made up of a cone and a cylinder. So perhaps in the first part of the question, you'll be asked to show this relationship H in terms of R, given the volume to be 60 unit cube. So the way to do it is, under the proof, would be to systematically work through it. So the volume is equals to, now the volume of the cylinder is pi r squared h, the base area times the height. Then for the cone will be 1/3 pi r squared, and the height is 2r times 2r. Now I will simplify it. So pi r squared h. Here I would have 2/3 pi r cubed. Since h has to be the subject, I will then transpose this term to the left. So I would have pi r squared h equals to v minus 2/3 pi r cubed. So since v is given as 60, so I put it down as 60 minus 2/3 pi r cubed. Now h has to be the subject, so I'll divide the equation throughout by pi r squared. So I have h equals to 60 over pi r squared minus, now the pi r squared to divide pi r cubed, I'll get just the r. So I have 2r over 3. Compare this with what's asked for. You can see that the two are the same, and therefore we end it off with this word shown. Now in formulation, when we are asked for the surface area, which is noted here as A, denoted as A, we want the total surface area in terms of R. So you notice that H will appear, but we will be using substitution here of the H expression. So first of all, the surface area now we need to formulate it, because if we have an equation involving too many unknowns and too many variables, then it makes it impossible to work through the sum in maxima minima. As you know, if we have one independent variable, then we can differentiate it. The first derivative equated to 0 to find stationary value of, say, x. But if we have too many variables, like in this case, it could possibly be you have the h, you have the r, then there are two variables. And it's impossible at this level of our syllabus to consider that. So in formulation, we actually will reduce two or more variables to just one variable, so that we can proceed with the maxima and minima work. So formulation, we are looking at the surface area. So A is equals to, we have the top circular surface, and that is pi r squared. Then we have the curved surface of the cylinder. We have the circumference 2 pi r times the height h. Then we would have the the curved surface area of the cone. That is pi r l. Now L going to be settled, so we have to use the Pythagoras theorem to do just that. We know that the radius of the cylinder is r. We know the height of the cone 2r. Then for the slant height, we'll have L equals square root of the r squared plus the 2r bracket squared. That will give me 4r squared. Then, to simplify that, I get 5r squared in the square root. So, when I simplify it, I will have square root 5r. So, here, I have pi r squared plus 2 pi r. The h is to be replaced by this expression over here. I have 60 over pi r squared minus 2r over 3. Then plus, now the L is to be replaced by what I have here. So I have square root of 5, then pi r squared. Now simplify this expression further. These two can be added together now. I have 1 plus square root 5 pi r squared. Then this got to be simplified. Pi r divided by pi r squared. So basically I have, when I multiply in, 120 over r. Then for here, I will have 4 pi r squared over 3. So you can see this is another like term. So I can combine these two together, particularly with this 1 minus 4/3. 1 minus 4/3 is negative 1/3. So I will have square root 5 minus 1/3 bracket pi r squared plus 120 over r. You can see, if I need to differentiate this to obtain dA over dr, this is a nice form to go about. So this can be changed to 120 r to the power negative 1. Now we look at this particular case. We have a semicircle, and within the semicircle we have a rectangle. C and D are actually on the circumference of the semicircle. So we have AB equals to x cm and BC, which is the width of the rectangle, y cm, and the radius, well, is 6 cm. So it can be this point, the center of the semicircle, or center of the circle if you complete the semicircle into a circle. That point to C is 6. So what we need to do before we can even formulate this area of the rectangle in terms of x is to work out y in terms of x over there. The reason is that if we want the area of the rectangle in terms of x, the y will have to be substituted. So we need an equation involving y as a subject. So we have a very simplified diagram here, just focusing on the rectangle. So the C, the B, the A, the D. So this length here will be half of the length of AB. So which is half x cm. And the length CB is y cm. And the radius will be 6 cm. Now, this angle here is 90 degrees, so that make that triangle a right angle triangle. So we will have the longest side opposite the 90 degrees, 6 cm squared is equals to the y cm squared plus bracket half x squared. So here I have 36 y squared plus 1/4 x squared. So to make y the subject, I will have y squared equals to 36 minus 1/4 x squared. Now that can be simplified if I just group them up to something like this. 36 times 4 is 144 minus x squared over 4. So y will equal to, in this case, I will reject the negative. So I would just have the positive root of 144 minus x squared over 4. And this can be simplified further because square root 4 is 2. So I'll have 144 minus x squared square rooted over 2. So next is to embark on the formulation. And bear in mind, in the area formula, we will have only x in the expression. So A, in this case, we're talking about the area of the rectangle. We have the length, which is x cm, and the breadth y cm. So the area is simply just x times y. So in this case, the y is to be replaced by this expression. So I will have x times square root of 144 minus x squared over 2. Now, if I need to go on from here in order to do the first derivative, then another form will be very handy, that is half x times 144 minus x squared to the power of half. That will be a neater form in order to facilitate the ease of differentiation. So you can see in this little video segment, we have emphasized the point that in order to do your proof and the formulation well before the maxima minima work, you have to understand the importance of memorization of the mensuration formulae for the basic objects. And I would even go to the extent to say the two-dimensional figures as well, which is not covered here. So we come to the end of the video.